Now let's have an example for what we have discussed before and see how we can implement what we have understood or what we have explained before to a real example. Okay. So assume that we have a short post, as you can see here. It's a short post constructed from a hollow circular tube. As you can see, it's hollow. It is hollow circular tube. So the cross section here, it is having like a hollow circular tube of aluminum. Supports a compressive load of 26 kips. As you can see here, this is the force being applied. Okay, this is the force being applied here. It is 26k, and k here means that it is kips, kilopounds, as we said, kilopounds. So whenever that we are telling that this force is being applied, means that it is applied on the centroid. Okay, so it is applied on the centroid. So 26 kips being applied on the centroid on this hollow circular tube. The inner and outer diameter of the tube are D1 4 inches and D2 4.5 inches. So we have 4.5 the outer and we have 4 inches for the inner, respectively. And its length is 16 inch. This is the length, which is 16 inches. The shortening of the post, what is the meaning of the word shortening here? Exactly, shortening means that how much decrease in the length would be. The shortening of the post due to the load is measured as 0.012 inch. This means that already it has been measured. It has been measured. So under this load, let's clean everything. Under this load, there is shortening of 0.012 inch. Determine the compressive stress and strain. So we're talking about stress here, okay, and strain in the post. Okay, in this post, we're talking about this post now. Okay, disregard the weight of the post itself. This means that the post, we're going to assume that it is weightless and assume that the post does not buckle under the load. Assume that the post does not buckle. What is the meaning of this? It doesn't buckle. Buckle means that if we are looking to the circular tube, maybe it will make something better like this, failure better like this, buckling. So we are assuming that this is not a failure mode. We should not consider this. It will not buckle. All the load is going to be received axially, and the element is going to respond to this load through axial or normal or axial stresses and strains. Okay, so now we understood what is the meaning of buckling, that the post does not buckle. And the other thing is disregard the weight of the post itself, because it might have weight. So in order not to bother ourselves with adding additional mass or weight of the element to this force, we say that the element itself or the weight of the post itself is negligible, is not going to be considered. Okay, and assume that the post does not buckle under the load. Okay, now we understood everything. Just to keep in our mind our main equations. Okay, our main equations, because we want to determine the compressive stresses and strain. We want compressive stresses and strain. We have equation number 1, which is the normal stress, P over A, as we have explained in the previous video. And we have the epsilon, which is the strain, which is the elongation or the shortening over L, right? So here we want to determine the compressive stress and strain. Actually, if we're talking about compressive stress, this equation, we need to know P. What is P here? Exactly, it is 26K. And we want to know A. What is A? It is the area of the cross section. As we said, it is what? Take care of this word. Take care of this word. It is hollow. It's not, it is like hollow circular tube. Hollow circular tube. There is hollow from inside, so it is something like this, for example. Sorry for not drawing well. Okay, it's hard to draw with the mouse, but anyway, this is how we are going to find that. This is the, yes, here. So the thickness here is going to be the only part of the member that is going to develop the stresses for bearing or withstanding the force. So we need to get the area. Okay, so we need to get the area here. So we have the outer diameter, okay, which is D2, 4.5 inches, and we have the inner diameter, which is 4 inches. So we can get the area in between, and then substitute in this equation, we can obtain the compressive stress. Regarding the compressive strain, we need to go to the equation here. The equation is telling us that we need to know what? Exactly this part, which is the shortening. How much shortening we have? Yes, we have mentioned it. It is 0.012 inches. So here there is some shortening is going to take place. This 16 inch is going to go down here like this by this amount, which is 0.012 inches. Okay, and then we have L, which is the original length of the element, which is 16 inches. Okay, so this is the solution of this example. Let's go to the detailed solution of it. Okay, so first of all, assuming that the compressive load acts at the center of the hollow tube. This is very important. As I said, we are not assuming that the load is here, for example, because if it's here and the centroid is here, this means that there is bending moment. So we need to be careful and assume that the load is being applied at the center. Okay, we can use the equation, which is sigma P over A, equation 1-1, which is this equation here, okay, to calculate the normal stress, and the force B equals to 26K or 26,000 pounds. Take care of the conversion of units. And the cross-sectional area A is, so we need the cross-sectional area. Again, we want to get the numerator and denominator. The numerator is 26,000 and the denominator is going to be calculated, as you can see here. It is circular tube, so pi over 4 times d2, the outer diameter squared, minus d1, the inner diameter squared. So it equals to pi over 4, 4.5 inches squared minus 4.0 inches squared. This gives us 3.338 inches squared. Okay, so therefore the compressive stress in the post is going to be, the compressive stress in the post is going to be, as you can see here, P over A, which is 26,000 pounds over 3.3 inches squared. This gives us 7,790 psi, pound per square inch. Pound per square inch. Okay, so I hope that you have understood now how we can obtain the compressive stress. Remember that we are talking about normal stresses here. Okay, now let's go to the next part, which is related to the strain, the compressive strain from equation 1-2. Remember, we were talking about this one. Okay, so epsilon equals to delta over L. Delta already is given, which is 0.012 inch over 16 inches. This gives us this value, 750 times 10 to the power minus 6. Okay, so we are now having the normal compressive stress and normal compressive strain. We've obtained both of them. Take care that the stress has units, which is pound per square inches, but for strain it has no units. Okay, it's unitless, as we said before, because it is length, unit length over unit length. Thus stress and strain and the post have been calculated as we wanted. Note, as explained earlier, strain is a dimensionless quantity and no units are needed. No units are needed. For clarity, however, units are often given, even that there is no units here, but for clarity we can give some units. For example, we can put it in this way. In this example, epsilon could be written as 750 times 10 to minus 6 inch per inch. Okay, or instead of 10 to the power minus 6 inch, we can put it micro, something like this, micro inch. Okay, this would be understood also. This is going to be understood also in a better way. Okay, now I hope that we have understood this simple example, but really it is going to give us an understanding of what we have explained before. Let's jump into another example and see how we can do something else, but without numerical values. We are going to use only symbols. Okay. A circular steel rod of length L, as you can see, it's a circular steel rod. Here we are talking about rod. Okay, of length L and diameter D. Diameter is D here. Hangs in a mine shaft and holds an ore bucket of weight W. As you can see, there is a bucket here with weight of W at its lower end, as you can see here in the figure. Okay, so what we want to determine, first of all, obtain a formula for the maximum stress, which is sigma maximum. Take care of this word. Okay, maximum, we're talking about maximum stress, sigma maximum in the rod, taking into account the weight of the rod itself. Here we are going to take into account what? The weight of the rod. We're not going to neglect it as we have done in the previous example. Okay, so really it depends on the example. So we cannot ignore or we cannot neglect the weight of the member unless it is clearly mentioned about this. Okay. Okay. Now the second point that we want to determine is calculate the maximum stress if L equal to 40 meter and the diameter is 8 millimeter and the weight is 1.5 kilonewton. Okay, so the point is, in point A we want to obtain a formula for the maximum stress. Okay, in point B we are going to calculate the real maximum stress based on numerical values. So there are some numerical values are being given here, so we need to use them in order to obtain the maximum stress. Again, as I said many times, we need to think about the formula first, and then we can substitute with these numerical values. Okay, now let's see. Let's go to A, which is, as you can see it here, the maximum axial force, F maximum, in the rod occurs at the upper end and is equal to the weight W of the bucket plus the weight W node of the rod itself. The latter is equal to the weight density, gamma, of the steel times the volume V of the rod. Or, okay, now let's go and understand what is the point here. let me put it clearly for you. Actually, we are talking about we want sigma maximum, right? We want sigma maximum. If we go to the equation 1-1, the previous on the previous example, this means that we want to put something here in the numerator, which is the force applied and the area, right? In order to get the maximum of this fraction, we need to obtain the maximum here in the numerator. This means that the force must be maximum, right? The force must be maximum. Okay, you're going to ask me, what about the area? Should we put maximum here? It's not relevant here because A, it is constant. It is constant. There is nothing is going to be changed. But F maximum, it is going to be changed based on two different items. The first is W, which is the weight, okay, the weight of the bucket, and the second is going to be W node, which is the rod, or the weight of the rod itself. So we have two items here. Okay, so we have two items here. Okay, so actually it is depending on the rod cross-sectional area. It depends on the rod cross-sectional area. So here we are going to put, okay, the delta maximum equal to F maximum over the area, and this F maximum equals to two parts. The first one is exactly, it is the weight of the bucket plus the weight of the rod. Whenever we have a rod, we need to think about something, that it is a rod, so it is solid from inside. It has a cross-sectional area which is A. It has fixed, also it has length, original length, which is L, and it has density, right? It has a density which is gamma, right? So A times L, it gives us volume, times the density, it gives us what is the meaning of the density here? It is the weight per unit volume. So if we multiply the gamma density times the volume, it would give us the weight, right? It is going to give us the weight. So here, this is the what we are going to have, which is the W node, which is the weight of the rod. The weight of the rod equals to gamma times V, and this gamma is going to be something that we know it, so we need to have it as it is. Okay, so in which A, so gamma, it's the density of the material of the rod, A, it is the cross-sectional area of the rod, and L, it is the length of the rod. Therefore, the formula for the maximum stress from equation 1-1, if you remember equation 1-1, which is the stress, normal stresses, F maximum over area. So F maximum here, it is W plus gamma AL, this is the numerator, over A from the formula equation 1-1. This means that after rearrangement, we're going to have W over A, weight of the bucket over the cross-sectional area of the rod, plus the density of the rod times its length. This is the formula that we have. Well, it's clear everything. Now, this formula tells us something. Okay, this formula here, it tells us something, that the weight of the bucket, the area of the rod, the length of the rod, and the density of the rod is going to be different elements or different factors are contributing to the normal stress of this member. right? Well, the next step is, if I'm going to substitute with numerical values for these certain, for the certain parameters here, what I'm going to have at the end. This is what we are going to see in the next slide. Okay, remember, let's go back here. It says that B, calculate the maximum stress if L equal to 40, D equal to 8 millimeter, and the weight of the bucket is 1.5 kilonewton. Okay. So now, to calculate the maximum stress, we substitute numerical values into the preceding equation that we have obtained. This is the preceding equation, right? Okay. The cross-sectional area, A, equals to pi d squared over 4, right? He gives us D, so it is okay for us to obtain A, where D equal to 8 millimeters, so we can obtain A. And the weight density gamma of steel is 77 kilonewton per meter squared. Okay, so from where we can get it, supposedly it is something known, okay, or you can obtain it from the textbook, okay, from table H-1 in appendix H of our textbook. You can find it there. It is something common for steel. The density of steel is 77 kilonewton per meter cubed. Okay, and then based on that, this sigma maximum is going to be 1.5 kilonewton, which is already given for us. As I said here, it is given the weight of the bucket, okay, over, this is pi d squared over 4. This is the area, right? This is the area part, plus the remaining part here, which is what is the density of the steel times the length. From where I got this, go back, weight of the bucket over the area plus density of the steel times the L, okay, the length. Okay, so now everything is numerically known for us. Then we can substitute easily, and you're going to find that the value, the final value, take care of your units, please. Here it is megapascal, and here it is megapascal too. So we are going to end up with 32.9 megapascal. Okay, in this example, the weight of the rod contributes noticeably to the maximum stress and should not be disregarded. What is the meaning of this? If we go back here, delta maximum, it has two contributions. One from the bucket, one from the rod. So this is contributor number 1. This is contributor number 2, right? For the given numerical examples that we have here, these numerical examples, you need to think about something. The weight of the bucket is 1.5 kilonewton, which is not very high. And in the same time, the density of the steel is 77, right? 77, as we said here, it is 77 kilonewton per meter cubed, and its length is how much? 40 meters. Can you imagine? It is 40 meters, very long, very long. So when you think about it, you're going to find that here the weight of the rod contributes noticeably to the maximum stress and should not be disregarded, because this is the part that is going to be added due to the rod itself. It is 3.5, okay, almost more than, it is almost like 10%, okay, so it should not be disregarded. It's not negligible here, so we need to consider it. Okay, so this is the meaning of, or this is the requirement number B, and we have an idea now about the normal stress and normal strain through the two examples that we have explained in this video. Okay, thank you. This is what I have explained for this video. Two examples relating or looking to the normal stress and normal strain I hope that you have an idea now about how we can apply the normal stress and normal strain equations into a real life examples, and I hope that it would be easier for you later on to use these equations to get an understanding of normal stress and normal strain. Thank you, and see you in the next video.